Okay, let's go ahead and get started. So this is lecture 1. And this happens to me every semester that I teach this course. I try to look at relevant literature. I try to watch YouTube videos. I try to get a sense of how to describe machine learning to you as other people have taught it, right? And this mainly has to do from the fact that I never personally took a machine learning course. I became interested in data science after I attained my PhD. So I never knew of these things before that. But this is kind of beneficial in a way because I taught myself and therefore I have like my own personal experience with it. So instead of looking at what other people have done or even like writing down my thoughts, in order to like explain to you what machine learning is, I'm just going to talk at you. And if you have any questions, just speak up and I'll talk back with you. Okay? And then I'm going to try my best to describe what machine learning is as I know it. Okay. So the question at heart right now, so the question before we get started is, so what is machine learning? Now, if anyone has any idea what machine learning is, go ahead and speak. Tell me what you think machine learning is. If you've, I know all of you have heard about it as data science majors, but do you have a sense of what it might be?
I mean, in general, isn't it the ability for a program to be able to get better over time from learning from its mistakes in the most general way?
This is like a close definition of what machine learning might be. Anyone else?
Machines being able to complete tasks without a programmer telling it to do so.
Okay, I like that too. Anybody else? So the way that I view machine learning will most likely best be conveyed by me describing a model. Okay, and once I describe the model, then we can talk about what machine learning is. And for me, this is the best way to understand it. There's plenty of other ways or other descriptions of what machine learning is, but this is my way. So we're going to say, okay, suppose we have access to data. Okay, and the data set looks something like this. Suppose we have n data points. So this is data that we have. Okay, and so for each of these points here, so we have xi, comma, yi. So for each of these points, xi is a vector of features, and in the beginning, we're going to assume that we have labels for each of the data points, and that will be the yi. So yi is a label. Okay, so we have access to some collection of data, right? And for each data point, we have features of that data point, and then we also have a label of what type of data that is. Right, so maybe I can like elaborate a little bit here and say this is what type of data. Maybe that's a good way to describe it. Okay, and so if I look at a given point in my data set, I have features and I have a label. Okay, so what I'm going to say is that I have all possible features for this collection of data, right? So not just this collection of data, but any collection of data that belongs with this type, right? So I'm going to say that X is the collection of all possible features for this type of data. So all possible features. And the X values from our data belong in here somewhere. So like, we have like some piece of it that we know. So the X values, so each of these X values from these tuples is somewhere in the collection of all possible features of that data. Okay? And then we have our labels. And I'll call this Y. And Y is a set of all possible labels. And we have some instances of the labels in our data set. So maybe like something like right there. So right there, that'd be like the Y values from our data set. Okay. And here's the goal of machine learning right here. There's a function that takes as input features and maps to labels. And this right here, I'm going to call the target function. So this is the target function. Okay. Target function F. And F satisfies a very special property. So if X is in our set X, then F at X equals Y is the correct label for that given information about the features you're given. So in particular, there is some perfect function that if you give me features, it's going to give me a label, and that label is the correct label. So in particular, it should be the case that f of xi is equal to yi for all I equals 1 to n. Okay? There is some function that does this. And the goal of machine learning is to find the best approximation to that function. And we'll talk about this in a later lecture, but in order to like fall into the realm of machine learning, F cannot be known. The target function cannot be known. So our goal in machine learning find the best function g so that g sufficiently approximates the function f. And how do we do that? We use the data set D. So if we have access to some small portion in X, call it D, dx, right? We use that set of data together with the labels for that set of data. We use this information to try to approximate that. So we want G to approximate that function f. That's the goal of machine learning, to me. Now, I'm a mathematician. I like abstractions more so than concrete examples. It helps me kind of think about the underlying problem more. But hopefully, with the following examples, you'll see how the examples fall into this model, right? So what would be a case where this type of model would be useful? Well, suppose, for example, you have, say, maybe pictures of numbers. And labels for each picture. Okay. So pictures of, say, maybe, let me extend this a little bit, maybe handwritten numbers. And for each picture of a handwritten number, you have a label that says whether or not that picture is a 5, a 10, a 6, or any number. For simplicity, let's assume they're just digits, 0 through 9. And for each picture that you have, so you have a picture, which is like your X here. If that picture corresponds to a 5, then the label would be the number 5. So you can imagine, right, that there's no possible way to have every possible handwritten digit from every possible person. There's no way to do that. Even one person's going to write a 3 different than the last time they wrote it. So we only have some subset of all possible handwritten digits to look at. And we only have the labels for the examples we have. We only have some subset of that, right? So we need to know, right? Like, if we get, for example, a new picture, we get some new picture, right? We want to be able to determine what the label is for that new picture that we get. If we get, like, suppose the picture we get looks something like this. It's like, is that a 7 or is it a 2? But we want the function, so I'll say that that is a 2. I'll call it a 2. But we don't know the label. This is something that doesn't belong to the data set that we have. So we want to use the data that we do know to infer what this should be. So think about how humans learn, right? You don't wake up knowing what a desk is. you experience many instances of encountering desks. And over time, you learn that that's a desk, right? So, or with pictures of numbers, for example. Over time, you learn what a 2 looks like. You use data to infer, like you use previous data, which is like the data that you own, to infer what a new image of a 2 looks like, or that what a new image of a 2 is. So there is some best function, right? There is some best function that exists. But we will never be able to know that. If we could find that best function, then it's not in the realm of machine learning, and we'll get to that next lecture. But we want our function g to take as an input these features, like this picture is like a feature. There's a bunch of things. There's like a curve there. There's a little line right there. There's a bunch of features. So that's like the feature vector. We want this to be the correct label for that picture. And we don't know that correct label. We have no idea what that label is. But we do know the labels for a given subset in there. And using that, we want to design an algorithm that finds G. And G here, this G right there, that's going to be what I call a hypothesis. We want to find the best hypothesis possible. Okay? So I want you to speak up if this idea is not clear so far. We have a collection of data. We have features, which is like the input, what you observe, right? And then we have labels for those features. And we want to use that data to be able to make predictions on data that doesn't belong to us. Okay? Any questions on that? Okay. So let's go ahead and model this problem with a diagram. Okay. And I found this diagram from this textbook. I modify the notation, by the way, in this textbook. I'm not entirely sold on it, but I do love the way the first chapter of this reads as it pertains to modeling machine learning. Okay. So let's look at my modified version of what they present on page 4 of that book. Okay. So we have an unknown target function that we need to find. And that's going to be denoted by F. Okay. We have our training examples, the data that we own. So that's that set of information D. And again, we know the features, and for our purposes right now, we also know the labels. That's not always going to be the case, but when introducing machine learning, let's just go ahead and assume that we know the labels for those features. And I'm going to always adopt the standard. I'm going to make the notation capital N be standard for the number of data points that we own. Okay. Now, here, we're going to have a choice of learning algorithms. I'll call that script A. This is all possible algorithms that we can think of. And then here, this is going to be my hypothesis set. And I'll denote that by H. Okay. Now, with our training algorithms, with our training examples and our hypothesis set, we implement a learning algorithm to find the best hypothesis inside of this set, so that at some point after implementation of this algorithm, we have our final hypothesis. We want G to approximate that unknown target F. Which, by the way, this unknown target, which we'll talk about in later lectures, this is the perfect hypothesis function. So in a sense, you can think of this as generating the data that we have. Okay. Now, it's important to note that the hypothesis set has a bunch of different functions inside of it. And the G that we find is going to be contained inside of our hypothesis set. So G is an element of our hypothesis set. Okay. Now, it's important to note the cardinalities of each of these sets. This is a set of learning algorithms, that's a set of hypotheses, or a set of functions. This is a finite set. There's only one in here. So this is cardinality 1. We have exactly some finite set of data that we can observe that we own. There's infinitely many functions that we can choose from to form our hypothesis. There's infinitely many algorithms that we can choose. The goal of machine learning is to find the appropriate algorithms for a given hypothesis set, so that we can best approximate the target function. And think about it, like there's also like naive ways to do this, right? Like one machine learning algorithm, possibly, it's kind of like a dumb one, would be like, if I gave you this image, and then you just say that your hypothesis is going to be a random number between 0 and 9. That's a hypothesis, right? That's a function that spits out a label. So if you put that in, you just, oh no, sorry. It's probably not the best notation. So you put in the image of a 2, or that image that we have, and then we just say that that's like a random number between 0 and 9. That's a hypothesis. It's not going to be very good, but it's still a hypothesis. Okay? It still gives you something in the output space. And that's important to remember as well, is that G maps your input space, or your feature space, to Y, where Y is the set of all possible labels. Okay. Is this picture somewhat clear? Now, please speak up so I can interact with you a little bit here. Come on, guys, at least one of you. If it's not clear, we can talk about it some more.
I guess I understand the general concept, but it might make more sense if I saw it like applied.
Okay, and we'll get there soon.
Okay.
Okay. So let's look at how we can do this. How we can model this. This is just a general framework for understanding what machine learning is. Now we're going to look at some specific examples. And I think that we should look at, I just decided this right now, so hopefully I can remember everything. Come on, camera focus, okay. I think we should look at the hello world of machine learning, the perceptron. The perceptron learning algorithm. Which I will abbreviate with PL. This algorithm, before we get started, I should mention, is due to Rosenbaum. Can't remember if it's 1 T or 2 T's. This is roughly around 1950. And I should also mention that you can think of this as the beginning of artificial intelligence, AI. Okay, so let's suppose we have our data set. So we have data, it looks like this. This is where the notation gets tricky. I'm going to use superscripts instead of subscripts to count the number of elements in the data set that we own, the training data. So instead of putting a subscript 1, I'm going to put a 1 up there. And then instead of putting a subscript 1, put a 1 up there. We have n data points. Okay. Now, suppose we want to model. So maybe not, maybe that's jumping ahead too far. We just have features and we have labels. And let's make this simple. Let's make the label space, let's just make that -1 or +1. So the y values here are either -1 or +1. That's all they are. Okay. And X, or yeah, the feature space is a subset of d-dimensional space. So each of these x's here are vectors in d-dimensional space. Each of the y's are labels -1 and 1. And for a concrete example, we could maybe think about this famous iris data set of flowers. So suppose -1 is the flower. So the labels can correspond to flowers in this case, types of flowers. So label 1 would be maybe the Virginica flower. And label positive 1 could be the versicolor flower. Virginica, versicolor. So these are two different types of flowers. Okay. And the feature space here is going to consist of measurements of these flowers. So measurements of the flowers. Okay, so does the data make sense to you at this point? Each data point, so the X vector are measurements of the flower. The Y value is whether or not it's a Virginica or versicolor. Okay, so we have features and label. And there happens to be only two labels. In this case, we say that it's a binary classifier that we do. We're trying to classify if we get new features, we measure these features, can we predict whether or not it's that type or that type? That's the goal. Okay. So what we're going to do is we're going to imagine this as, I might be jumping ahead too much, but maybe imagine this as a neuron in our brain. So the way that neurons work is neurons receive signals, and if these signals are beyond a certain threshold, the neuron fires, and it passes the signal along. Okay, so what I'm going to say is that maybe we can say, let's think about this. Let's say, let W be a D-dimensional vector. And we're going to say that these are going to be weights. Okay. And we're going to say something like this. If the linear product of the weight, so W transpose times X, because remember these are vectors, right? If that's greater than some threshold, we're going to say that that's going to indicate 1. Okay. And if it's not greater than some threshold, it's not going to fire. So that's the threshold again. Then we're going to choose that the output is -1. Okay, so let's pause for a moment. We have some weights. We don't know what those weights are, but we do know what X is. So if we pick any feature vector, and let's go ahead and say this. Let me adopt some notation. We're going to predict Y hat. So Y hat is our prediction. So if the linear combination is greater than some threshold, we predict 1. If the linear combination is less than that threshold, we predict -1. So we have what's happening here is that we're taking the features of the flower in this case, and we're weighting each of those features. And if the combination of summing all those features together with the weights is high enough, the neuron is going to fire. Okay. And this is often depicted with an image many of you probably have seen online. So if we only have two features, so if we suppose X is a subset of R2, then we only have two measurements to work with. Okay, so let's suppose that, right? So another way to think about this value here is to look at this diagram. Okay. So weight 1, weight 2. And what do we feed into this diagram? We say that x1 we feed in there, and x2 we feed in there.
Are these x1s and x2s the same because you use a subscript instead of a superscript?
Yeah, so let me actually, thank you for
Okay.
calling that to my attention. So we feed in xi. So that's xi. And that's measurement 1, that's measurement 2 for that feature vector.
Okay.
Okay. And this is going to predict some value. And so, well, what do we feed into this neuron? We feed in a linear combination of this vector times this vector. Weight 1 times x1 plus weight 2 times x2, sum that, right? But then we need to figure out how we're going to choose. So I wrote it up here. If this combination is greater than the threshold, we do 1. If it's less than the threshold, we do -1, right? So what we're going to do is we're going to choose something called the sine function. So I apologize, I'm running out of room and I'm going to have to erase. I was supposed to have another chalkboard delivered yesterday. So hopefully by next class I'll have 2 and I won't have to erase so much. So bear with me on this. So we're going to say let -b equal the threshold. Okay. And B is what we're going to refer to as a bias. Okay. So then we can look at the following. So if W transpose times X plus B is greater than 0, Y hat is equal to +1. So if that's -b, just add positive b to both sides, and you get this equation here. If W transpose times X plus B is less than 0, we want Y hat to be -1. Okay. So you see, if this is equal to -b, we just add b on both sides, we get these equations here.
Where do we get the weights from?
We have no idea what those weights are, and we're going to come back to that in a moment.
Okay.
Okay. So another way of looking at this would be, well, may I erase up there at the top? Do all of you have that written down?
You're
Okay.
gonna post this video, right?
Yes.
Okay, yes, you can erase.
So what we're going to do is say something like this. We're going to modify, so I should actually, like, let me write out what this looks like. So W transpose times X plus B is like saying W1 times X1 plus W2 times X2 plus B. And we're assuming that we only have two features to work with. Okay. So just to make things notationally easier, we're going to modify our weights in our X. So we can write this as one term without the B. Okay. And this happens a lot when you're looking through the literature where things get so cumbersome and messy that you want to make things as concise as possible. So what we're going to do is we're going to say that, so if xi is equal to the vector xi1, xi2, then x bar I is equal to the vector 1.0, xi1, xi2. So we're going to modify x this way, and you'll see why in a moment. And if w is equal to w1, w2, then w bar is equal to w1, w2, w3. Okay.
Wait, could you kind of explain why those are different vectors?
Oh, sorry, this should be w3. Well, the reason why is this right now. So then W transpose times X plus B is then equivalent to, where is it? Oh, wait a minute. B, W1, W2. So then this is equivalent to X, sorry, W bar transpose times X bar. It's just it's a way to simplify it so we don't have to deal with the bias. We can treat the bias like a weight, basically. Do you see that these are going to be the same though? Because when you take the product of X bar with, so if you take W bar transpose times X bar, then we get 1 times B plus X1 times W1 plus X2 times W2. So do you agree that this is the same as that now? Are we good?
Yeah, I think so.
It was just a way of simplifying this. So now what we're going to say, so this y hat is just a single prediction, but we want to find our best hypothesis, that function g, right? So we're going to say that g of x is equal to the sine of W bar transpose times X bar. And the sign is simply, if it's positive, do 1. If it's negative, do -1. So I'll go ahead and write that out. So that's 1 if W bar transpose times X is greater than 0, -1 if W bar transpose X bar is less than 0. So you see that this right here is doing exactly what we wanted. We just needed to kind of write it really formally to convey the idea. Okay. So now, if we pass in a given vector X, this is going to spit out G of that vector. And we want this to approximate Y. And this right here, this is the target function. So this is the target, and this is our hypothesis. Okay? So under the pretense of trying to classify these flowers, right? We pass in some features. Those features have weights that correspond to them. And if the weights are big enough, then we're going to say this sign function will return a 1, right? If the weighted value is greater than 0, we return a 1. If the weighted value is less than 0, we return a -1. So in this instance here, this is just saying predict Virginica. And in this case here, we're predicting the flowers of first color. Okay. But now we have to return back to a question that a student just posed a second ago. What about the weights? Well, what we know, if we look back to the diagram that I erased prior, we had that box, right, where we had our hypothesis space. H. Now, notice that this function is going to differ based off of the weights that you choose, right? If the weights are all 0, that's 1, right? If the weights, if the first entry was a 1 and the second entry was a 0 and the third entry was a 2, which, by the way, the bias now you can consider a weight, so we don't have to talk about bias anymore. We can just say the weight, right? Among all possible weights, right, there's an infinite choice of weights. But among all possible weights, some are going to do better than others at predicting the correct output. Okay, so now this is where we go into the algorithm part. So for the algorithm, we need to choose the best weights. That's the goal. Among all possible weights, there are going to be weights that will give us the best predictions. And we want to pick the best weights so that we can approximate our target function y. Okay? So how do we do this? Okay. Okay, so let's talk about the actual algorithm now. So given a data point xy, compute y hat equals to the sine of w bar transpose times x. Okay. Now here's the step. If y hat does not equal the label. So by the way, this data point is in our data set that we have, the data that we own. Okay. So if that's the case, we're going to update our weights. Our weights will be updated according to and this is the Perceptron update rule. So just pause for a moment and think that y hat was our predicted outcome, right? So if this is in our data set, we know the label for that feature vector. So if we predict y hat and it's not equal to the correct label, we know that we didn't do well. We didn't make the right prediction. So we're going to change our weights so that we get closer to making the right prediction. Okay. So, and we also know, by the way, that y hat is always equal to the sine of, oh, by the way, back to that, W bar, the W that takes into account the bias. Okay. And I haven't really dived into this model here, this picture. That will come later in the semester. But when you look online and you look at Perceptron, you're probably going to see this. So I just wanted to draw it for you. But we will go into much more detail about neurons when we get to deep learning. Okay. So I have to, some of you must be thinking that this update rule, so doesn't this seem arbitrary? Doesn't that rule seem arbitrary? Like, what is that doing? We're changing our weights by updating them with this formula here. Okay, the weights then become this. So how does this, why would this seem reasonable to do to update our weights? Okay, let's talk about why this update rule is reasonable. So why is Perceptron update rule reasonable? So let's suppose, okay, now you have to bear with me on this. Suppose that we misclassified. We predicted a 1 and it should have been a -1, for example. Or we predicted a -1 and it should have been a +1. So case 1, y hat is equal to 1, but y is equal to -1. And recall that the only two labels that we have are either +1 or -1. Suppose that's the case. Okay. Well, we need to recall a formula that I guarantee most of you have forgotten about dot products. So if you take the dot product of any two vectors, not just w and x, but any two vectors, this is equal to the magnitude of w, is magnitude of x, times the cosine of the angle between them. And these are vectors, right? So this is the angle between the vectors. So what determines the sign of the dot product? The only thing that determines whether or not the product is positive or negative is what? Cosine of the angle between the vectors. That's the only thing, because that's positive, that's positive. The only thing that determines whether it's less than 0 or greater than 0 is that. Are y'all with me on that? This is the product and it's equal to this. That's positive, that's positive. The only thing that could be possibly negative is that, right?
Yeah.
The angle between them.
Yeah.
So if you recall from basic facts about trig, okay, so if the angle is less than 90, right, then cosine is going to be positive. It's the x values, right? If the angle is greater than 90 and less than 180, cosine is going to be negative. If the angle is less than 270, it's also negative. Cosine is always negative over here in quadrant 2 and quadrant 3. But then if it wraps back around over here, then it's positive again. Does that make sense? Right? That's just the values of cosine, whether or not it's positive or negative. Right? It's 0 at 90, 0 at 270, but it's positive over here, negative over there. So if we're looking at, if we predict that, right, but it should have been a -1, so what happens? So if we predict that, then it must be the case that W bar transpose times X bar. If we predict a positive one, we know that the dot product between those vectors is greater than 0, right? Which means that if it's greater than 0, the angle between the vectors should be something like this. So if this is like X bar, this could be like W bar. The angle between them is less than 90 degrees. Okay? So what's happening here with it? We have W and we're going to change it somehow, right? And we're going to change it according to this update rule. So what is the value of y hat? It's 1, right? So it's just going to be 1 times x. Okay. Oh, I almost made a mistake here. Or did I? Let me make sure. Yeah. This is, as soon as I drew the picture, I realized that something was off. It's not y hat, it's y. And this is why it's y. So y here is -1. So we're not using y hat here, we're using y. -1 times that vector x. So let's look at where the new w is. Okay. Instead of writing this arrow, I can say this just to make it more clear. Our new set of weights is equal to our old set of weights plus that. Okay. So let's look at this. So here's x, right? Here's w. So what are we going to do? We're going to subtract x from w, and we can use that tail rule from linear algebra. So we go up here, and then this is subtracting off x. So then look what happens. When we subtract x from w, look at the angle between these two now. Is that angle greater than 90 degrees?
Yeah.
So now when we look at w bar transpose times, so w bar new times x bar, the angle is greater than 90, which means that that cosine is going to be negative, right? So now that, which means that the new prediction that we make with our new weights, so it's like the new one that we make, is now going to be -1. And look, what did we do? We fixed the weights for that one example that we passed in, right? So in this case, for the one example, x, y, we fixed the weights, fixed them. So the next time that we encounter that data point, because we did this update rule, our new w is going to be at an angle greater than 90 with our feature vector, our modified feature vector. So the output that we're going to do is going to be the correct one. Does that make sense?
Yeah.
You see that by subtracting w, we made a new weight vector that would output a negative example, a negative value. Okay. So now let's look at the other case. Part 2, that's negative and that's positive. So part 2. So we predict a negative one, but the actual label was a positive one. So they don't match up, so we do the rule. Our new weights are equal to our old weights plus y times the feature vector that we're considering. So in this case, we predicted a -1, so we know that W bar transpose times X bar for the given data point that we feed in, we know that that was less than 0. And again, this is our old weights. Because the value is less than 0, we know something about the angle between the vector X bar and W bar. We know if this is X bar, we know that the angle goes something like this. And this is our old set of weights. So then our new set of weights is equal to our old set of weights plus y, which is just 1, times our feature vector for that given instance. So where is W new? We'll go to the head of W old. So we take X, put it there. So then W old plus X is going to be over here. So now what is the angle between those vectors? Doesn't it look like it's less than 90? Right? So then, so then now if we look at W bar new transpose times X bar, now if it's less than 90, that means that this output is going to have a value greater than 0, which means that our new predicted Y is going to be equal to 1. So that and that now match up. Does that make sense? So we fixed our old weights. The next time that we encounter the data point XY where we originally messed up on, the next time we see it, we have a better chance of predicting the actual correct output. So in the chat box over here, can everyone type yes if they feel like they get the reason why this is reasonable to fix the weights, and no if you don't. And if you don't, I'm going to make another video for all of you who don't understand it. But the general reason is that the angle between the vectors is bad, so we fix it by closing it in if it was above 90. If it was below 90, but we needed it to be above, then we fix it the other way.
I had a quick question.
Yes.
Now, when we're changing the weight, and we're changing it case by case basis. So if we were to, when we change the weight and we get a new X to predict, are we going to stick with that weight and change it again if it needs to be to try to get closer, or does it just
Yes,
vary?
good point. And I'm glad that you brought that up because that's exactly where I was going. So you're going to update every time you encounter a collection of features that predicts the wrong output. That's how the algorithm is going to work. So now that we understand that for a given one instance, so far we've only talked about fixing it on one instance at a time, right? As you were just pointing out. So how does this work? So the algorithm, we're going to initialize W bar randomly. Okay, so actually, okay. And then for each XY in our data set that we own, if Y hat does not equal Y, W bar becomes W bar plus Y times X bar. Okay? So yes, each instance we treat separate than the other instances. But regardless, if we misclassify, we still update those same weights. And again, that goes back to the model that we have, right? We have so again, if we're going back to our flower example, we have weights 2, 8, 3, and then X bar is passed in here. And in here, we're going to pass just 1. And here, we're going to pass X1. And then here, we're going to pass X2. And we can think of that as like a column vector. We take a linear combination of those values with the weights, and then we apply the sine function, which that's the graph of the sine function, by the way. So the graph of the sine function looks like this, where this is 1 and that's -1. That's why I write it like that. And then we output a y. So for each of these, we pass in, we look. If we need to fix our weights, we do. And then we look at another one, pass it in. We have an output. If we need to fix our weights, we fix our weights. Okay. And it turns out if the data is linearly separable, the Perceptron learning algorithm will find a solution, find a perfect solution for G, the approximation to the best solution. It will separate the data. If we're looking at a binary classifier and it's linearly separable, then we can do that. It will find that separator. So those are the general steps for the algorithm. Okay. Now, I think right now is a good time to take a short break, like a 10-minute break. because now that we understand how the algorithm works, we're going to actually implement it. I'm going to code it for you. Okay. So in between now and when the video picks back up, I'm just going to pause the recording and I'm going to leave Zoom on, by the way. It might be beneficial if you pull up a Julia Jupyter notebook, if you want to program Julia with me. And it might be beneficial if you're not doing that, pull up a Python Jupyter notebook and get access to the iris data set. If you're using R, get access to the iris data set. And I'm going to walk you through how to do this step by step from scratch. Okay. So I'm pausing the video. Okay, so let's actually implement this algorithm. So we're supposing that we have two-dimensional feature vectors, and it's a binary classification problem. 1 if it's type this, -1 if it's the other type. Okay, so the way that this works, so we're going to initialize W bar, which is a three-dimensional vector randomly. And 2 for each data point x, y in your observable data set, a form x bar, which is equal to the column vector 1.0, comma x1, comma x2. So that's a column vector. And then part B, if the sign of W transpose bar times X bar does not equal Y, then update W bar with W bar goes to W bar plus Y times X hat. Okay. And one way that we can do this is we can choose what's called an epoch. So if, say, so epoch equals K, repeat 2 K times. We're not going to talk about error measures today. We're just going to say an epoch is you run through the data set that you have once. Every piece of data in that data set, run through it one time. That's one epoch. If you have K epochs, you run through the data set K times. Okay. So take a moment to have that written down on your paper so I can share my screen with you. And I noticed that the W bar notation is kind of cumbersome right now. The only reason why we're using that right now is it stems from what I was talking about earlier by starting with the weights and the threshold. In the future, we're just going to use W without the bar. Right? If you have a d-dimensional vector, feature vector X, we're just going to assume that the weights will be d plus 1 dimensional. And we can just drop the bar notation altogether. So I'll give you a few more moments to do this. I should say that 3 maybe is your output or your hypothesis. So your output is your function g of x, which is equal to the sine of this. And this is going to be your final hypothesis. And our hope is that this is going to approximate, or not y, approximate the target function. But 1, 2, and 3, that's the algorithm. Okay. So give me one moment to pull up my notebook. So one moment, please. Okay. Share my screen. Okay, so I apologize. I should have done this during the break. The first few moments it's going to take a little while. So I'm using Julia version 1.0.5. Okay. So I'm using our data sets. And then I'm also going to use the plots package. Okay. So this is going to take a moment to run. So I apologize for that. As many of you know, the first time that you import packages in Julia, it takes a moment for them to run. Okay. So I am curious, is anyone not using Julia right now?
Yes, I'm using Python.
Okay.
Yeah, I'm also using Python.
All right, that's cool. Python's a great language. I just personally, for me, I prefer Julia when coding things from scratch. Okay, so now I'm going to access the iris data set by saying iris is equal to data set, and then I'll say iris. Oh no, I got to mention data sets, and then the iris data set. Okay. So again, the first time you run these functions, so data set is a function from this package here. So the first time you do that, this is always going to take a moment, at least with Julia. But after you do it one time, then Julia becomes very fast. All right, so this reads in a data frame, a Julia data frame. So we have measurements of the flowers. So these are the iris flowers. We have setosa, and then, well, we can't see everything else. But we can access columns like by calling dot and then the name of the column. So if I just did iris dot and species, so that gives me all the species. So I know ahead of time that my data set, I know the first 50 are setosa, and I know that the second collection of 50 are versicolor. Okay, so setosa and versicolor. And we're going to try to classify two of the flowers, so setosa and versicolor, based off of only two measurements. And we get to choose whichever two we want. We can have sepal length, sepal width, petal length, petal width. So I'm going to choose that our features are going to be these two values here. So I'm going to say x, or yeah, x data is equal to the array of tuples x for x in zip, which most of you should be familiar with zip. Zip iris dot sepal length from 1 to 100, and then iris dot sepal width from 1 to 100. Okay. So we have features. These are just numerical values, and these are measurements of sepal length and sepal width. And now I need the labels for those. But notice that the labels are not numeric. They're not 1 or -1. They're strings. So I need to just convert those to numeric values, either 1 or -1. So I'm going to say y data is equal to, I'm going to use what's called a ternary operator here. So I'm going to say y equals to versi color. If that's true, I'm going to return a 1. And if not, I'm going to return a -1. And this is for y and iris dot species 1 to 100. So now, instead of versi color, I have labels that are -1 or 1. Okay. So if y is equal to versi color, then it's a 1. Otherwise, it's a -1. Okay. And if I look at the first 50 species again, there's Setosa. So Setosas are labeled -1, versi color, or 1. So actually, I'm going to do that. I'm going to do Setosa instead of versi color. That's what I'm used to doing. So Setosa. And now the Setosas have label 1, versi colors have label -1. Okay. So this is just getting my data ready. So now I want to look at a plot of this data. So I'm going to say scatter. And I'm going to say x data from 1 to 50. And I know that that data corresponds to Setosa. I'm going to say label equals Setosa. And I'm going to give this color blue. And then I'm going to label my axis. So I'm going to say x-axis equals to sepal length. And then I'm going to say my y-axis is equal to sepal width. Okay. And then I'm going to give it a title equals to iris data. And we're looking at Setosa and versi color. So Setosa and versi color. So that's just scattering the first 50 points. So that's only doing Setosa. So I need to layer on top of that the other data. X data 51 to 100. And these are labeled versi color. And then I'm going to give these the color red. See what that looks like. Again, I'm using the scatter function for the first time, so it's going to be slow at first. Okay, so there's our data. So we have measurements, sepal length versus sepal width. They're all plotted here. And then we know the labels of this data. So we can say that these are Setosa, these are versi color. And also we see that the data is linearly separable. There is a line that separates that data. Okay. So now we just need to define our functions so that we can implement the PLA or the perceptron learning algorithm. So first, I'm going to say function. I'm going to call this the sign, and it's going to take in weights and a value feature vector x. And we're going to have to make our x bar. So by the way, if you've never seen that before, I just do x and then backslash bar to get that little bar over it. And that's going to be equal to 1.0, comma, x1, comma, x2. So if you're not familiar with Julia, indices start at 1 in Julia. And then we're going to return the ternary operator. So we're going to have weight transpose times x bar, so backslash bar tab. So if that is greater than 0, question mark, return a 1, otherwise return a -1. So that's the ternary operator, okay, in that function out. So then I want to define a function that implements the perceptron update rule. So we'll say function perceptron update rule. And this is going to take in weights, a feature vector, and a label for that feature vector. And we're going to say if the sign of weight, comma, x, oh, sorry, the sign is not equal to y, okay, the sign is not equal to y, we want to update the weights. So weights plus equals y times x bar. So we can say, we can just write it out. So x, so no, 1.0, comma, x1, comma, x2. That's like x bar. Okay. And then in that if statement and say return weight. So that's it. That's the perceptron update rule. Okay. All right. So now let's write a function to implement the algorithm. OA, perceptron learning algorithm. And that's going to take in, say, a data set X and a data set Y. And then I'm going to give it an optional keyword, say epochs. I'm going to set that equal to 1,000 by default. Okay. So then W is going to be a random collection of values from a normal distribution. That's why I put it in there. So that gives me a random 3-dimensional vector from a normal distribution. Okay. So then we just have to do the for loop. So say maybe for a while, so counter equals to 1, maybe, and say while counter is less than the number of epochs, just perform the update rule. W is equal to perceptron update rule. We're going to pass in W. Oh, I need to go through all the values in X and Y. Right? So for I equals 1 to the length of X, we're going to apply the update rule to xi, comma, I. So this is the feature for this label. So features for that label. And we're going to end that for loop and then do counter plus equals 1 and then end the while loop. And then we're going to return W and then end the function. So if I didn't make any mistakes, I think that's it. Okay. So now let's just go ahead and play around with it. So let's say W is equal to PLA of X data, comma, Y data. And then let's say box equals to 10. Okay. Now, what's going on here? Well, if I look to my board, what we really have, right, is we have 1 times 1.0 times weight 1 plus W1 times X, or this is W2, sorry, times X1 plus W3 times X2. This is some function in 3-dimensional space, is some plane, right? So what we're going to do, since we're only concerned about X1 and X2, 2-dimensional space, and this is a line in 3 dimensions of plane, we just want to project this down onto the 2-dimensional space to see if we split the data. So we just set this equal to 0, and then we solve for X2. So what does X2 become? So X2 is like a function Y. So X2, so going to be negative W2 times X1 minus W1 all divided by W3. So if we set that the Z value equal to 0, then we're projecting onto the plane, and then we just solve for X2 and treat that as a function of Y, and we can plot it. I think that's it. Did I do that right? So subtract that on both sides, subtract that on both sides, we get that, and then divide by W3. Okay. So this is going to be a line in 2-dimensional space. Okay. So share my screen again. All right, so let's look at what that line looks like. So we already have a plot up here, so I'm going to plot on top of that. And I'm going to plot X, comma, negative W2 times X minus W1 all divided by W3. So, and these are tuples that I'm plotting. And that's, I'm just going to say 4x equals 2 to 7 or something. I know that the data set up here, well, maybe 3 to 7. Yeah, okay, 3 to 7. I'm looking at the x values. Okay. And then I'm going to give this a label equal to learn so learned split 1 or something like that. So this is the projection of that plane onto the 2-dimensional space And it doesn't do anything. Like, it doesn't separate this at all, right? It's just all on that side. But what if I change the number of times I go through the data set? What if I change that to like 50? And then let me do this again, and I'll call the new line 50. Line split 50. Oh, we're doing something, right? This was better when we did it 50 times, when we ran through the data 50 times. What about if we do it 100 times? So I'll call this one 100. So there's the, oh, I need to do that. There it is. Oh, it's starting to separate the data. So what if I do it 1,000 times? If I run through the data 1,000 times. That red line, see it there? So let me go back up here, and I'm gonna plot that again. And then I'm gonna run this 1,000 times. And then I'm gonna plot that. Look at that line there. See how it's splitting the data? So if you're on this side, you're Setosa. If you're on this side, you're Versailles color. That's what the Perceptron learning algorithm is doing. It's learning a linear separator, a line that separates the values. So now we can write a function, say function predictor. You put in some weights and you put in some measurements, x, and some features. And then we're going to say something like, so return sign of weight x. So if that equals 1, we're going to say that that's a Versailles color. Otherwise, oh no, Setosa, sorry. Setosa. Otherwise, we're going to say it's a Versailles color. I think that'll work. So let's look at y data 30. Or actually, let's do iris dot species 30. Setosa. Let's look at what our predictor does. Let's look at iris dot. What are we going to do? So predictor w, comma, we'll pass in iris dot sepal length 30. This needs to be a tuple. And then iris dot sepal width. So this is what we predicted. And we can just do this again. So I'm going to copy that. Put that in there. Copy that. Paint line that in there. And then we just play around with it. What if we put in an 86? 86. So the actual label, the true label is, and then the predicted label is, and we can just change this up, maybe put like 96 in there, 96 in there, 96 in there. So maybe I can say k is equal to a range from 1 to 100, and then just pass k in there. So that's a random integer between 1 and 100. Isn't that cool? We've learned, or the algorithm learned. It learned to pick the correct weights that gave us the desired hypothesis that approximates this perfect target function that we don't know, that we'll never be able to know. Okay. And if I just keep on doing this, in fact, just looking at the picture on this data set, this line is always going to, the learned weights is always going to predict the correct label. Okay. Okay. So I'm going to stop the recording now. And the next video lecture will pick up next week. So